Okay, hello students. So in today's lecture, we are going to learn about the packing efficiency. Okay, so I'm going to share here the PPT. In the last lecture, we are up to the three-dimensional arrangement of the crystal structure. Okay, now in today's lecture, we are going to we are going to learn about the packing efficiency. Now, in what is mean by packing efficiency? For that, you must know the type of the crystal. In the last lecture, we are up to the coordination number of the HCP structure, then CCP structure, and also we have learned about the three-dimensional structure that is of the tetrahedroids, then the square close packed layers, which results in the simple cubic primitive cubic unit cell. Okay, we have learned this structure, and then in the next lecture we have learned about the tetrahedroids and octahedroids, and then we have learned also that the play packing of the hexagonal close packed layer in the three dimension, which results in the HCP structure, and by the arrangement, two different types of arrangement, that is A and B, and that will result into the structure that is the hexagonal close packed structure, that is the HCP structure here. And when we place the third layer, that is the C layer, and that will gives you a total different structure, that is the FCC structure of the cubic close packed structure. Okay, so in this way we have learned the three types of arrangement of the crystal structure, that is HCP simple cubic, then the HCP structure hexagonal close packed structure, that is AB pattern, and the CCP structure or the HCP structure, uh, that is the result of the ABC type of packing of the hexagonal close pack layer in three dimension. Okay, we have also learned that the coordination number is 12 for the HCP and the CCP structure, and it is 6 for the simple cubic structure or the primitive cubic structure. Okay, now we are going to learn that how these atoms or the spheres they are arranged in a unit cell. If they are arranged in a unit cell very closely packed, then the efficiency of the unit cell is large, or the effectively the unit cell is packed. Okay, and if these spheres they are arranged not that much effective way, then the efficiency is less. Okay, or we can say that there is a more voids are present in the unit cell, or the empty space is there in the unit cell. Okay, so efficiency will decide that the how closely, how compactly the given unit cell is filled with the sphere. We can say that it is filled with the spheres. Okay, so we are going to learn now the packing efficiency of the unit cell. Which unit cell? Simple cubic, simple or primitive cubic unit cell, then body structured BCC unit cell, and the HCP structure or FCC structure. We can say that FCC structure, the packing efficiency. Okay, so in your syllabus, only the we have to study about only the packing efficiency of simple or primitive cubic unit cell and body center cubic unit cell. Okay, and the third one is deleted for this year. For the packing efficiency, what is mean by packing efficiency? It is the fraction of the total space occupied by the spheres. Oh, so in the unit cell, the volume of the unit cell is fixed, and because it is having that geometric shape, and how much sphere is occupied by the unit cell, that will concern with the volume occupied by the particles actually in the unit cell, because unit cell contains the particles, and whatever space occupied by the particles is called as the volume occupied by the particles in the unit cell, and this divided by the total volume of the unit cell, that results in the packing efficiency. So the definition of the packing efficiency is it is the fraction of the total space occupied by the spheres or the particles. Okay. Now, if you multiply this by the 100, then we get the percentage in terms of the packing efficiency in terms of the percentage. Okay. Let us study about the packing efficiency of the metal crystal in simple cubic lattice. Okay. For the simple cubic lattice, this is a very important diagram. This diagram is of the one of the face of the simple cubic structure unit cell, that is the cube. So it is a, like a very very popular structure like a cube, and cube is having the how many faces? Six faces. So one of the face of the cube is like this. Okay. For the simple cubic unit cell, and this is the these are the spheres, that is the particles which are at the corner. So for this one of the face, these are the particles present at the corners, and they are actually the touching to each other, because we are considering here the packing efficiency of the metal crystal. So because of these are the metal crystal, all the spheres are homogeneous, they are of same size. Okay. Because they are metal crystal, and here we can say that if they are touching each other, these are the rigid spheres. Okay. And here this represent the radius of the sphere. So this half of the edge length, this complete, this is called as edge length A, here represented here A, and half of the distance of the edge length is R, one of the radius of the one sphere, and the second half is the again the radius of the second sphere. So A is equal to nothing but 2R. Okay. So here we can say that first step we are going to study this in the four steps. Okay. So first step is to calculate the radius of the sphere. So radius of the sphere is very easy from this diagram. So diagrams are important for so as to understand the packing efficiency. Only for this chapter, the diagrams are important for the packing efficiency. Okay. So here we can easily write that A is equal to 2R, or R is equal to A by 2. Okay. Now next is the this R here represents the radius of the atom, and A is the edge length of the unit cell. Second step is the volume of the sphere. Now, how to calculate volume of each sphere? Okay. And for this the formula is, because it is a round in shape, these are the rigid spheres. So volume of the sphere is 4 upon 3, or 4 by 3 formula is 4 by 3 pi r cube. Okay. So this is the well-known formula, and here we just replace the r by simply a by 2, because r is equal to a by 2. So replace r by a by 2. So this is 4 upon 3 pi, and this r is a by 2. So what it gives, the step 3. Okay. So using this r in the form of a by 2, we get here the volume of the particles as just extend this as 4 into a, because a cube, and pi remains as it. Okay. And this is in the denominator is 3. Okay. And remember that this is 4 upon 3 pi. Okay. And this is not 3 pi, huh? So this is 4 upon 3 pi. So pi is in the numerator, 3 is in the denominator, 4 is in the numerator, then a, that is a cube, and the cube of the 2 is 2 into 2 into 2. So overall reduce this, and we get here pi a cube upon 6. This is the volume of the one particle. Okay. Now we know that simple cubic or primitive cubic unit cell contains only one particle. Okay. We have already calculated this. Okay. So because of this, the total volume of the particles remains the same, because this is the volume of the one sphere. And if the unit cell contains only one sphere, then the total volume of the particles in the unit cell becomes pi a cube upon 6. Okay. So remember that the first step is to calculate the radius of the atom. Second step is to calculate the volume of the one of the sphere. Third step is to calculate the total volume of the sphere. So just simply multiply by the number of particles present in the unit cell. Okay, and then the last step is the packing efficiency. So it is very easy to calculate the packing efficiency in the fourth step. So there are total four steps. Because if you divide this in the step 4, it will be easy. So packing efficiency is nothing but pi a cube, means this formula. Okay, total volume of the particles in the unit cell. Okay, pi a cube divided by 6, divided by the volume of the unit cell, because the shape of the unit cell is cubic. Okay, so volume of the unit cell becomes a cube and multiplied by 100. Okay, so this is simple, that if the unit cell is cubical and it contains one particle, so packing efficiency is the volume of that particle divided by the total volume of the unit cell. Understood this? Total volume of the unit cell is simply a cube. So this, and we multiplied by 100, we get 100 pi, reduce this, we get 100 pi upon 6, put the value of pi as 3.14, and we get here the answer is 52.36%. If you are multiplying by 100, we get the answer in percentage. Okay, so this is very simple. You just remember the steps: step 1, step 2, step 3, and step 4, and we get the answer. Okay, so if the empty space then becomes 100 minus 52.36, it becomes 47.64%. Understood this? So void or gap, or the volume of the unit cell which remain, which is empty, or which is not, you know, which is not, which does not contain a sphere, or it is empty one, empty space. Okay, that is 47.64%. So we can say that it is how much compact it is, that will be decided if you go for the next type of unit cell, that is called as a packing efficiency of the metal crystal in the body centered cubic lattice. Okay. So here the diagram is important. First is you try to understand the diagram, that where the spheres are touching. Okay. Now even if this is the body centered cubic geometry is cubical, but here the unit cell is a specific, that is body centered cubic, in which the arrangement of the particles are only not only at the corner also, and at the center of the unit cell also. So these are the particles at the corners A, and this is center of the sphere A, and center F of the sphere, next sphere. Okay, and this is the center of the sphere, that is C. Okay, so here the sphere is present at the center of the cube, and also all the 8 corners, also the spheres are present. Okay, here it is not shown so as to avoid the complication here. Okay, so we are at the face, they are not touching each other. At the face for the BCC unit cell, the spheres are not touching at the face. Okay, even they are present at the corner of the face, they are not touching at the face. Okay, so there is a slight difference in the they are not touching from the primitive cubic unit, so there is a slight different in the arrangement of the spheres. Okay, and but they are touching to each other at the diagonal, at the one of the diagonal, there are two diagonal for the cubic geometry. Okay, internal diagonal, can you understand? This is the internal diagonal, this is one, and one is next, second is this one. Okay, so they both at the both this, they are the corners spheres are touching to the center sphere at the diagonal position. So here in this image, this is shown as this is shown as where the spheres are exactly touching, and we are going to find out the diagonal first. This is the important step. We are going to find out the diagonal. Okay, because diagonal here is 4r. Why it is 4r? Even if it is given in this diagram, like these are the spheres, this is not the exact position of the spheres. They are at the they are at the corners, at the center of the corners. Okay, and here the diagonal is 4r, and this 4r we are supposed to calculate in terms of the edge length. how much is the 4r. Okay, so that's why we can do this with the simple mathematics, and that's why we are writing here the point. This is the point D and this is the point E. This is the center of one of the sphere at the corner is A. Center of the sphere at the center of the unit cell is C. The center of the sphere at another corner is F. So this is the diagonal actually. And now first step is to calculate the radius of the sphere. So for this, we are taking the two triangle for triangle FED. So take this triangle FE and the base at the which is at the face which is at the base. Okay. So FED triangle, here in this triangle the angle only the same angle FED. So this angle is of 90. Every angle is 90 degree. Okay, and here if it is 90 degree, then according to Pythagoras we can write here theorem that FD square is equal to FE square and DED square or DE square. So FD square is equal to FE square plus ED square. Put the value of FE. So FE is A, edge length, we know this. AED is also the edge length, okay, because it is cubical geometry also. So A square plus A square become 2A square. So we get here this FD. FD is coming as 2A square. FD square is coming as 2A square. This is important. And once we know the FD, okay, so we get here for triangle, this triangle now FAD or AFD. This take this triangle AF and D. For this triangle, the same angle ADF, AD and F. The triangle AD and F. First we have taken this angle and now we get go for this angle. Okay, ADF. This is again the 90 degree. Okay, and for to calculate FA, we are interested to calculate the FA, that is the diagonal, inner diagonal, and that is 4R. We know this because this R, then this is again R, this is again R, and this is again the R. So total it becomes 4R. So we are supposed to be here AF square is equal to AD square. Okay, because this is the angle. So again, according to Pythagoras theorem, FD square, AD square plus FD square. So easy. So try to understand that which angle we are to taken, and ultimately we are interested to calculate the FA, that is the diagonal. So we get here A square plus 2A square, and because FD we got here in the first equation, the step 1, put the value, that is 2A square. So A square plus 2A square is 3A square, and we are interested in AF because this is AF square. So F is under root 3A. AF is equal to under root 3A. So what we get AF? We get the distance AF, that is the inner diagonal, that comes as root 3A, but that is equivalent to 4R. So we directly write here that root 3A is equal to 4R. So R is equal to root 3A upon 4. So R is equal to root 3A upon 4. This is very important step. Okay. Now step 2 is again calculate the volume of the sphere in the same way. So 4 upon 3 pi r cube is the formula to calculate the volume of the sphere, and then go for the volume of one particle. So put the value of r, we get the volume of one sphere or one particle, that is 4 upon 3 pi into bracket root 3a upon 4, that is because this is the r radius, and this is the cubic. Okay, and here just put the value here. So 4 upon 3 pi root 3 cube, a cube divided by cube of 64 is 64. 4 is 64. So by reducing this, we get here 4 into root 3 into root 3, okay, into root 3 pi, then a cube divided by 3 into 64, and we get here root 3 pi a cube upon 60. We get the answer as root 3 pi a cube upon 16. And in the step 3, we know that BCC structure contains two particles. The number of particles present in the BCC is two particles. So just this is the volume of one of the particle or one of the sphere. Multiplied this by 2, we get root 3 pi a cube upon a. This is very easy. root 3 pi a cube upon t multiplied by the factor 2. Okay, and now we get the fourth step is packing efficiency. So volume occupied by the particles in the unit cell divided by the total volume of the unit cell, and this is multiplied by 100, we get the answer. So put the value of root 3 pi a cube upon 8 upon a cube. So put the value of pi and multiplied by 100, we get the answer 68%. So there is no need of calculation. You can simply write it as 68% and in the step 4. And if it is 68%, then the empty space or the void volume is 32%. How it is 32%? 100 minus 32 is, sorry, 100 minus 68 is 32%. So this is the packing efficiency of body centered cubic cell. And from this, we can say that the simple cubic unit cell is less compactly occupied by the spheres, but body centered cubic unit cell is more compactly arranged by the sphere. So their body centered unit cell or crystal structure is more and more compact. We know that for the solids, if they are more closely packed, the density is more. The density is more. Okay, and if they are loosely packed, okay, so this is packing efficiency. They are loosely packed, the density is less. Okay, and we have also learned how to calculate the density, the formula. Okay, now this is the packing efficiency for the cell, and I'm going to show you again the same diagram here. If you don't understand, this is the best representation for the body centered cubic cell. And what I am trying to say that this is the sphere which is present at the center of the BCC unit cell. These are the corners, 1/8 part of each corner, we know this. Okay, and we are taking, these are the two diagonals, and you can say from this diagram that they are touching at the diagonal. The spheres are exactly touching at the diagonal. So you can say that here, this is the three, spheres. They are touching at the diagonal side, and for this we are calculating actually the first, that is at the basement, that is root 2a. Okay, and then we calculate the root 3, that is the diagonal here. The value comes as root 3a. Okay, and from that we are calculating the distance. So we actually we calculated this root 3a is equal to 4r, and from that we calculate the r, and we are putting the value of r, and here we get the 0.68. Multiplied this by 100, we get the um, packing efficiency as 68%. Here it is not multiplied by 100. So by multiplying 100, we get the packing efficiency as 68% for the body centered cubic unit cell. So diagrams are important. Even if you go for this diagram, it is it is it is okay. Okay, and here also whatever in the textbook, you can go to that from that diagram to calculate the packing efficiency of body centered cubic unit cell. Okay, so we make here the chart, and from the chart you have to remember that for the, because we have to learn the simple cubic unit cell and body centered cubic unit cell or the lattice, and for this the coordination number is 6 and the packing efficiency is 52.36% for the simple cubic unit cell. For the metal crystal and for the body centered cubic unit cell, the coordination number here is 8. Okay, and the packing efficiency is 68%. The packing efficiency is 68%. Okay, so this way it is easy to find out from this the packing efficiency and the empty space. Okay, and I think we will stop here, and in the next lecture we will go for the next topic, that is the point defect. Okay, so in the next lecture we will going to see about the point defect. Till then, you should take care and goodbye.